Hi everyone, I'm excited to present our paper, FairFlow, Mitigating Dataset Biases Through Undecided Learning for Natural Language Understanding. Language models are prone to dataset biases. These biases are shortcut solutions that models pick up during training, such as features that spuriously correlate with specific labels. In practice, a biased model may perform well enough on the in-domain test set, but on out-of-domain or challenging test sets, the biased model may suffer from significant performance degradation and performs just slightly better than random guessing. These dataset biases may come in different formats. For example, in natural language inference tasks, high lexical overlap between premise and hypothesis may spuriously correlate with the class entailment. Biases can also appear in different formats, such as that are not easily detectable by humans, or in other formats that we don't know. Therefore, we need debiasing methods to make language models robust, and robust to different types of biases. Let's first have a look at how existing methods work. Most existing debiasing methods follow a two-step approach. First, they train a biased model to capture the biases in the dataset, such as hypothesis-only bias in EMNLI dataset, and unknown biases captured by a weak model or less trained model. Then the biased model is used to measure the amount of input bias and regularize the confidence of the target model through some debiasing objective, such as product of experts in this case. However, we notice that bias can appear in different formats from different sources, not just the hypothesis part. This paradigm is strongly limited by a single source of bias, and we have to make assumptions of the type of bias a priori, making these models fail in practical scenarios. In this work, we propose undecided learning, a novel debiasing method. The idea of our method builds upon the behavior of a robust model. When given intact inputs with enough information, a robust model should be confident about the correct label. On the other hand, when given known biased inputs or corrupted inputs where there's not enough information, a robust model should remain undecided about the label. The objective of undecided learning is to effectively regularize models' behavior when processing inputs with biases. Let's look at an example of natural language inference task where the goal is to decide the relationship between the premise and the hypothesis. When given both premise and hypothesis, we encourage the model to be confident about the correct label. When given a biased or corrupted input, such as empty premise, we encourage the model to be undecided about the label. Notice that the input may still be a valid sentence, in this case the hypothesis. However, the NLI task requires both premise and hypothesis to correctly predict their relationship. In this case, the required information is missing. Therefore, the model should remain undecided about the relationship. Similarly, biased inputs can also be implicitly created, which we will go through later. Our method consists of two steps. First, creating known biased inputs, and secondly, undecided learning with a novel debiasing loss. We first design a series of perturbations to create known biased inputs for the robust models to learn from. In explicit perturbations, we directly modify the input text to create biased inputs, while in implicit perturbations, we modify the representations without touching the input. We will walk you through an example of an NLI task. Given the original input text, we feed it into the NLI model and get the intact representation. In sub-input perturbation, we drop some of the constituents of the input, making it insufficient to decide a label based on the corrupted text, such as dropping the hypothesis. Then we feed the explicitly corrupted text into the model to obtain the biased representation. This perturbation targets the sub-input bias. Notice that sub-input bias can occur in any constituent of the input depending on tasks and datasets. Our method does not require any prior knowledge of which part may contain sub-input biases and which part may not. This is a major advantage over existing works. We also design ungrammatical perturbations where the inputs are significantly shuffled such that corrupted text does not contain enough semantics for a robust model to decide the relationship. In addition to explicit perturbations, we also need to handle implicit biases which are not easily detectable by human. We design two types of implicit perturbations. In representation-based perturbation, we use the original intact input, but significantly corrupt the representation, such as zeroing out 90% of the elements, resulting in a biased representation. We can also deactivate the model, leading to a significantly less capable model and a biased representation. With the created biased inputs, we then design a contrastive learning loss to encourage the model to be undecided about the labels and the biased representations. Let's assume in the NLI task, we're given 6 input examples. Each dot here represents a representation of an example whose label is annotated by color. We apply a single perturbation, creating another 6 representations colored in red. We then group the representations by color and encourage examples within the same group to be similar to each other and examples across different groups to be dissimilar. In the perturbed group, we include an extra node, which is the uniform distribution across all classes. In this way, when facing perturbed representations, the model is encouraged to predict all class equally confident, similar to the uniform distribution, which achieves the goal of undecided learning. This can also be extended to multiple perturbations. In addition to debiasing contrastive loss, our framework supports any other existing debiasing objective, then combines biased representations to train robust models, such as product of experts, debiasing focal loss, and confidence regularization. Now let's look at some results. We evaluate each model on in-domain test sets, challenging test sets including stress and OOD, as well as transfer test sets. Fine-tune denotes the standard fine-tuning without any debiasing method. FairFlow refers to our model of applying 2 perturbations plus debiasing contrastive loss, which shows performance improvements over fine-tune and other baselines consistently on different test sets. We notice that some recent debiasing methods may hurt in-domain performances, while FairFlow does not, which is crucial in real applications. We also notice that FairFlow helps zero-shot transfer performance without outperforming all baselines by 2.9 points on average. Compared to methods that assume a single source of bias, FairFlow shows improvements on all test sets. This is because bias can appear in different formats and from different sources. We do not restrict our model in those aspects, making it robust and capable of handling various types of biases. Then we did 2 ablation studies, adding perturbations from a vanilla model and removing perturbations from the full model. We find that all perturbations are helpful to debiasing performances. In the meantime, it does not hurt in-domain performances. We also notice that different perturbations have different contributions because they all have their own assumptions and inductive biases. Next, we compare different debiasing objectives. When using the same perturbations, our debiasing contrastive loss outperforms product of experts, and debiasing focal loss on all test sets. And it is effective across a wide range of language models and tasks, including natural language inference, paraphrase identification, and relation classification. Additionally, FairFlow does not overfit to specific types of biases. We test different debiasing methods on different types of challenging test sets, created with different heuristics and rules. FairFlow shows the highest average performance and lowest performance variation across different sets. This demonstrates that FairFlow can generalize to different types of biases. We attribute this to the diverse perturbation capturing a wide range of biases and undecided learning objective we propose, which provides effective regularization of model behavior. In summary, we propose a novel debiasing method called undecided learning, which says given known biased inputs, a robust model should remain undecided about the label because there is no enough information. The biased inputs are obtained with a series of perturbations we design, which targets both implicit and explicit biases. Finally, FairFlow demonstrates significant performance improvements over existing debiased methods over a wide range of language models and tasks. We encourage you to check our paper and code. Thank you.